Hello everyone, today we are going to discuss Unit 2 of Control System, Block Diagrams and Signal Flow Graph. Here, content of Unit 2, Block Diagrams and Signal Flow Graphs is divided into two parts, that is A part and B part. Block diagram prediction and numericals will discuss in A part. In B part, signal flow graph, Mason's gain formula for deriving the overall transfer function of systems, feedback characteristics of control system, concept of negative and positive feedback, sensitivity of system to the parameter variation using negative and positive feedback. Feedback characteristics we have discussed in Unit 1 also, and in this unit also we have to discuss this. Just moving towards A part. So first of all, we'll discuss the block diagram. In given problem, they'll give you a complicated diagram and we have to just eliminate that complicated diagram and we have to simplify this diagram like this: input, output and one block. So there are some rules to do this. Let's see the rules. Cascade or series connection. If in given problem there are blocks in series, we'll just simplify the series block directly by multiplication, G1, G2 and G3. Let's discuss this in detail. R of S is the input and C of S is the output. Here G1, G2, G3 blocks are in series. X2, X1, these are the branches. So how we are just going to calculate this X2 mathematically? Just multiply the previous gains which are coming to this point, that is R of S into G1 of S is nothing but X2 of S. How we are just going to calculate X1 of S? Signals coming to this point, G2, G1 into R of S. Then how we are just going to calculate C of S? G3, G2, G1 and R of S. So what will be the equivalent diagram after simplification? Just input and output, make a one block and just write the multiplication of the block gains into this G1, G2 and G3. Now parallel connection. We can see this diagram. In this diagram, R of S and C of S is here. G1, G2, G3 blocks are in series. X1, X2, X3. This R of S and C of S. G1, G2, G3 blocks are in parallel. So now we have to calculate X1, X2 and X3. So just multiply these previous signals, G1 and R of S, that is X1, X2S, R of S into G2 of S, R of S into G3 of S. These are added by this summing point. So how we are just going to calculate the C of S? This G1 of S, G2 of S, G3 of S into R of S. So just simplify this diagram. R of S, if like this diagram is there, so R of S will be plus or minus G1, plus or minus G2, plus or minus G3 and C of S. Means this complicated diagram we can write like this in a simple block, in one block. So feedback connections, R of S, C of S, this is feedback loop. We can see from this takeoff point, this is shifted to this summing point, this is feedback loop. We have discussed the formula for this in Unit 1, that is system upon 1. If here is minus, make it plus. If here is plus, make it minus. System upon, here is minus, so 1 plus system into feedback. So what will be the answer? G of S upon 1 plus G of S into H of S. This is the formula. Now how we are just going to calculate the characteristic equation. Equate the denominator with the 0. Equate this denominator with the 0. We'll get this equation. Now moving towards next, block diagram algebra for summing points. Now here we can see we have to move this summing point to the right hand side. So g of s will be added to this. If we want to move this summing point to the left hand side, so 1 by g of s will be added into the system. Then fifth, block diagram algebra for pick or takeoff points. If you wanna move this takeoff point after the block, then 1 by g will be added to this signals. If you wanna move this takeoff point before a block, that is to the left, so g of s will be added to the system. Now reduction rules, we have to strictly follow this 6 steps. First of all, when problem is given, we'll follow these steps. Combine all cascade loops. Second, combine all parallel loops. Eliminate all minor feedback loops. Then shifting, try to shift your summing point to the left. You can shift it to the right also, but the diagram will be complicated then. So try to shift your summing point as far as possible to the left and try to shift your takeoff point to the right. Repeat steps 1 to 5 until the canonical form is obtained. So some basic rules with the block diagram transformation. We have to remember this chart also. First is combining blocks in cascade or series. G1 and G2 are in series. X and Y are the inputs. So just make this G1, G2. Combining blocks in parallel. If G1, G2 are represented by the forward loops, we can make G1 plus or minus G2. Moving the pick-off point, moving this pick-off point ahead of this block, behind of this block, or to the right hand side, so 1 by g will be added into the system. If moving this takeoff point before a block, so 1 by g will be added into this, g will be added into the system. If you wanna move this summing point after a block, so g will be added into the system. If moving this summing point before a block, 1 by g will be added into the system. Remember these 4-5 rules, very important. Now let's see one example. First of all, observe the diagram. Observe this diagram. In this, input is given, output is given, summing points is given, 2 takeoff points are given, G1, G2, G3, H and Kc. So these rules states that first of all, combine loops. See in problem, if there are combined series blocks, first of all combine that. Then secondly, combine parallel blocks. Eliminate the minor feedback loop. Try to shift summing point to the left. Try to shift takeoff point to the right. After every simplification, repeat from 1 to 5. Now let's solve the problem. In this problem, is there the series loop or cascade loop? No. Is there the parallel loop? No. So I can see here it is a feedback loop. So some of you may be think like this, G1 and G3 are in series, but the rule is like this. Between any series or parallel blocks, there should not be any summing point or takeoff point. Then only we can consider that in series or parallel. Here in this case, G1 and G3, in between that, this is the takeoff point. So we can't consider this in series. So no series block, no parallel blocks. So this is the minor feedback loop. So how we'll just remove this minor feedback loop? We know the formula that system upon 1 plus or minus system into feedback. So system G1 upon, here is sign minus, so it will become plus here, system G1 into G2. So what will happen? G1 upon 1 plus G1 into G2. So I have simplified this minor loop like this. So now we can see this KC, this block and G3 is in series. Just take it into the one block and just take this to the one block. Now we can observe that this is the minor feedback loop. If I want to combine this in a one block, I have to just take this into the one block and finally simplify the feedback loop. So what will happen? We know system upon 1 plus system into feedback. Just simplify this calculation, we'll get this answer. Now moving towards next problem. First of all, observe the diagram. Follow the 5 rules. R of S, G1 of S, G2 of S, G3 of S, C of S. These are the feedbacks to this summing point. One takeoff point. So first of all, I am observing G2 and G3 are in series. Now this H1, H2, H3 are in parallel. So our rule says that first of all make this as a combined series loop. So what will happen? G2 into G3. So make this calculation H1, H2, H3. Reverse these signs. Here will be the minus. So now I am observing this is the feedback loop. So what is the formula for the feedback loop? System upon 1, if here is minus, plus system into feedback. So we have written, we have just calculated this as this. So after removing this minor feedback loop, this and this block will be in series. So what will happen? Just multiply this G1 by this. Just simplify these calculations. You will get this answer. I hope you have understood this. Now moving towards SFG. Signal flow graph. In this introduction to signal flow graphs, definitions, terminologies, Mason's gain formula. Signal flow graph, alternative method to block diagram representation developed by Samuel Jefferson Mason. It is also called as S.J. Mason. Block diagram are adequate for the representation of cumbersome. A signal flow graph provides the relation between system variables without requiring any reduction procedure. Fundamentals of signal flow graph. Consider a simple equation below. Draw the signal flow graph for that. So y is equals to ax is the equation. So we can draw the signal flow graph for this. This x is input, y is output. Y by x we know the transfer function. X is input, y is output, and this is the gain. Now important terminologies, branches. Line joining two nodes is called as branches. X is node, y is node, and this is called as branch, which is joining these two nodes. A branch having one can be added at input as well as output. We have to add two dummy nodes, that is for one for input and one for output. Input node, it is node that has only outgoing branches. This This is having only outgoing branches. Input that has only output that has only incoming branches. We can see by this diagram. Forward path. Any path of input to output node, from input to output node, any path in a forward direction. So we can see here dark blue line, these are two forward paths. Loop. A closed path from a node to same node is called as loop. This point is starting from this node, ending at this node. This is this is one G2 into this is one loop. G2 into H1 of S will be the loop gain. G4 into H2 of S will be the second loop gain. Third loop gain, this loop. G4, G5 and H3, this yellow loop. Then finally this G4, G6 and H3. In this way we can calculate the loop and loop gain. Self loop, the node, the feedback that contains of only one node is called as self loop, starting from that point and ending at that point. What is loop gain? The product of all the gains forming a loop, that is nothing but loop gain. We can see here red mark, A32 into A23 will be the loop gain. Then path. A path is a traversal of connected branches in the direction of branch arrow. Path gain, the product of all branch gains while going through the forward path is called as path gain. What is feedback path or loop? We can see here x2 to x7, this, x6 to x5, x6 to x5 to x4 to x3 to x2. Touching loops. Observe this diagram. When two loops are having this common node, that loops are touching loops. Here we can see L1 and L2 are the loops. Both loops are combined by these nodes, L3 and L4 loops. Both loops are combined by this node,